C, application engineer at Ramaiah Skill Academy, and your speaker for today. Okay, and I'm excited to walk you through the amazing world of digital circuits and hardware coding. Okay, but let's first start with a simple thought. Suppose, imagine you're building a robot, not from the Lego blocks, but real working hardware with processors, memory, logic circuits, etc. How would you tell the robot's brain what to do? Can you do it by drawing it on a paper? Maybe for a smaller circuit like a switch or a multiplexer, yes, you can do. But what if you're designing a smartphone processor or an AI chip? You would need to describe millions of connections, right? Which you cannot possibly do it manually. That is where hardware description languages, or in short, HDLs, come into picture. Okay, so this is what we are going to cover in this entire session. We'll understand what is Verilog and its importance, how Verilog differs from VHDL, what is Verilog's role in RTL design flow, its syntax and few key concepts, and what is the difference between simulation and synthesis. I'll show you one live demo of one simple circuit that you can design it at your end. Okay, and other courses that we offer at RSA and our upcoming webinar details. Okay, now, so you know that today's chips have millions and billions of logic gates, right? And verifying them manually is almost impossible because you cannot meet the time to market that the industry requires right now. And there will be a lot of human errors. That is why manual designing using only schematics become obsolete. Okay, what the industry requires now is a way to describe the circuits using code. That is where HDLs came into picture. But what is HDL? HDL, as we call it, hardware description language, we use it to describe, design, simulate, and verify the digital circuits. Right. So they describe, unlike the other programming languages like Python or C, HDLs don't describe what a computer should do. They describe how the hardware should work and how it should be built. Okay, think of it like writing a blueprint of a circuit, not just the algorithm, but we are making a blueprint. Okay, now there are several popular HDLs available like VHDL, which we call it as VHSIC, Very High Scale Integrated Circuit, HDL, Verilog HDL, System Verilog, System C, My HDL, etc. Our focus in this entire session will be on Verilog HDL. Okay, because it is simple, powerful, and it is very extensively used in the industry. Now, what are the key features of HDL? As I said, instead of drawing the schematics, circuits are written in simple text. We call it as code. And it supports multiple abstraction levels also. And it is modular, reusable designs that scales from simple gates to complex systems. Okay, and it allows testing of circuits before fabrication, because once the circuit is fabricated and you have the chip with you, then you cannot do anything if it goes wrong. Before it goes to the fabrication, you need to make sure that your circuit is free of bugs. All right, so that is where the hardware description languages helps you in testing the circuits before the fabrication. Okay, now, as I said, why manual digital circuit is impractical? Because today's chips, we have millions and millions of gates. If it some gate connections between two gates, if it goes wrong, so you cannot sit manually and check between which gate there is a problem, which wire has a problem, right? Which gate is damaged. So it increases the complexity, and it is very difficult to verify also. Right. And again, time to market is a major issue that it demands. That is why industry demands faster design cycles. That is where HDLs have been proved themselves to improve the design cycle. Okay. Now, as I said, there are many hardware description languages like VHDL, Verilog, System Verilog. But why specifically Verilog? Because Verilog is very similar to the C programming language and very easy to learn. Okay, it allows us to do text-based hardware modelings. Okay, instead of drawing schematics and everything, we can just type what we want the circuit to do. Okay, so that it is reusable, modular, and scalable circuit design. It can be extendable to any number of logic gates. Okay, and synthesis and verification can be automated using the Verilog HDL. And if you want to work with the FPGA and ASIC flows, Verilog is very supportive. Okay, so I must tell you, Verilog isn't just used in labs or textbooks. It covers real world technology that you use every day. And compared to VHDL, it is very less verbose. Okay, so these are few applications of Verilog HDL. It is used in the ASIC design. ASIC design that starts from the chip specification till the fabrication. So like processors, you are developing AI chips or digital signal processing. Like in your smartphones, you have a small chip that is designed using Verilog HDL and the complete ASIC design flow. Okay, and if you want to work with FPGA based system, then Verilog is the easiest way to work with it. Okay, and in system on chip is multiple blocks together that are brought together in one chip or one layout. Okay, to work with system on chip also Verilog is very helpful. And you can also inculcate AI ML accelerators or any other technique from the machine learning. So that also you can inculcate with Verilog. Okay, for example, Google's tensor processing unit, it is also designed in Verilog. All right. Now, what is the basic difference that is between Verilog and VHDL? Verilog, as I told, it is similar to C programming. So very simple to program, very easy to learn also and to program also. And it supports design and simulation and also supports the synthesis part. And it's very popular in all of the industries right now. Okay, Verilog is majorly used for designing purpose and system Verilog for verification purpose. Whereas VHDL, it is more popular in industries like NASA, NAL, okay, etc. And it is more very verbose. It's very lengthy programming compared to Verilog programming. So if you are aware of VHDL, then it is very easy for you to learn Verilog. And if you are aware of Verilog, then yes, of course, you can learn VHDL, but it is very lengthy. So compared to VHDL, Verilog is very easy to learn and program. Okay. Now, where exactly this Verilog fits in the RTL design? So as this Verilog, we can say, is a best entry point if you're starting to enter into ASIC or FPGA industries quickly. Okay, so because ASIC design flow, it starts from specifications, as you can see on your screens. So this is the ASIC design flow. It starts from specification, then we decide what the architecture it needs, what are the blocks it needs, okay, what each block performs, and then each of this block will be implemented using RTL design, which is nothing but Verilog coding. Okay, so RTL design is the entry point for your design ASIC flow. Okay, then once you have designed this RTL coding, then you simulate it. That is, you verify whether whatever you have done is correct or not. Your chip works as per your requirements. Then you generate this coding, whatever you have written in terms of logic gates. Okay, because at the end, what we see on the chip is nothing but the gates. Right. So you have to convert your coding into logic gates. That is what is called as synthesis. Now, once your synthesis is done, then we follow the physical design process. Okay, like floor planning, power planning, CTS, routing. Then we check for the errors like DRC, LVS. Okay, once everything is verified, everything is clean and error-free, then we generate what we call it as GDS2 file. This GDS2 file will be sent to the fabrication team where they develop or manufacture the chips in bulk quantity. Okay, so Verilog is a bridge between your design intent or the design specification and the hardware realization. Okay, so it supports both functional and gate level synthesis. And one of the strengths of this Verilog is that it supports multiple abstraction levels. This makes it easier to design, debug, and optimize. Now, hierarchical modeling. What does it mean in Verilog? Hierarchy means it can either be from top to bottom or bottom to out. Correct. So Verilog supports both top-down as well as bottom-up approach. It will help us to design complex systems also very easily. Suppose I have a CPU. CPU will contain ALU, registers, memories, etc. Right? So I can take a specification of a CPU, what it should contain, and then I will divide it into multiple blocks like ALU, registers, memories, and then I will design these multiple blocks individually. I will design an ALU individually in Verilog, registers individually in Verilog, then memories in Verilog, and then integrate all together and then make it a bigger circuit called a CPU, right? So this we do so that it mimics real hardware design, how the hardware looks after it is manufactured. Okay, so top-down approach, as I said, from the CPU, then we go for the ALU registers, the smaller blocks, and then implement this logic gates. ALU in terms of logic gates, registers in terms of logic gates, control units in terms of logic gates, and then everything will be inculcated or integrated into one CPU architecture. Okay, it helps in very early stage of verification because you're defining a bigger structure beforehand. If anything goes wrong, you can design what are the blocks you need, how many blocks you need. You can decide beforehand. So it helps in early stage verification. Okay, so this is how the top-down design flow looks like. There's a top level blocks which you have divided into sub blocks, and this sub blocks can again be divided into another sub blocks. The last sub blocks we call it as leaf cell. Okay, that is in terms of logic gates. Bottom up is just the reverse of it. Okay, so you have suppose you have designed a full adder. You can use that full adder and then make it a ripple carry adder. That is, you can integrate 4 full adders to form a parallel adder or a ripple carry adder. This ripple carry adder can be used inside an ALU to do the additions of 4 bits or 8 bits or 16 bits numbers, right? So you have taken a small block and then integrated it into to form a bigger block. Okay, so why this is helpful is since you have a smaller blocks at the first, you can test the smaller components at very early stages. So it is very easy to test. Whereas in top-down approach, what happens? You have a complete structure at first, and then you have to divide it into multiple blocks. So you cannot check the smaller blocks, what you have designed inside it, because you already have the top approach, right? So bottom up design will give you, will allow you to test independent components, smaller components, and then unit level verification. Okay, so this is how first you design the gates and then the ALU or full adder, and then use it to form the ripple carry adder, then into ALU. Okay. So this is what I discussed. So top-down approach starts from the system level, that is the top level, and then goes into bottom, the smaller levels. Okay, so it allows for early stage verification, but difficult in later stages because you have already integrated the components from the top module. So it will be very difficult to take it out and then verify it and then put it back together. Okay, so for the larger scale, if you have a larger circuit, then this will be better approach. Whereas bottom up starts from the smaller components. So you can verify that smaller components first, whether it is working or not, and then use it to build the bigger modules. So unit testing is possible. Now, Verilog has different abstraction levels. Okay, so it supports 5 abstraction levels. One is behavioral, data flow, gate level, switch level, and structural modeling. Behavioral level is the highest abstraction level in the Verilog. It gives you the algorithmic description, how the circuit behaves. That is given by the behavioral structure, what the circuit should do, like a flow chart or an algorithm. Okay, so behavioral level discusses that. Data flow, how the data flows from input to output or from one block to another block. Okay, so it's very simple way of writing the code in data flow level compared to any other abstraction levels. Gate level, in other ways, it discusses, deals with the logic gates. Okay, netlist is nothing but the logic gates. Okay, this deals with the specific types of gates and the how the gates are connected. Okay, and switch level is the lowest level which models the transistors and interconnects. Okay, so transistor level modeling like NMOS, PMOS, okay, VDD, ground, all this will be dealt with the switch level modeling. And what is structural level? Structural level, you have seen the top-down approach and bottom-up approach. You have a full adder, then a ripple carry adder, then an ALU. So my main module is ALU. The submodules are ripple carry adder, and another submodule of ripple carry adder is full adder. So I can design one full adder and replicate that full adder multiple times in my top module. Okay, so this will simplify the way we write the code and also the complexity of the circuit. So this is done in structural level. Okay, so this is how a Verilog module looks like. Basically, you have a module. We have to give a name to the module, right? So module is a keyword. Then you write a module name, and then you write a port list. Okay, module name, suppose ALU or full adder. Then port list are the inputs and outputs of that module. Suppose for a full adder, you have 3 inputs A, B, C, and 2 outputs, sum and carry. So all this will come inside this port list. And every module ends with end module. For example, I've given here ripple carry counter. For counter, it's a sequential circuit, right? So we need to have a clock and reset, and the output of that is Q. So inside this module and end module, you will have your logics. Okay, so apart from this module, end module, and port list, we also have several other functions that is within the Verilog module. One such thing is declaration of the wires and reg. I will tell you what is wire and reg. Okay, and as I said, data flow, behavioral, structural, switch level modeling, everything will come within the module and end module block. Okay, and instantiation of lower level modules is nothing but the structural level designing. And we have something called the tasks and function, which performs a specific set of function. Okay, that also will be given inside this module and end module. So this is how in general Verilog module would look like. So now let us understand this abstraction levels a little bit more briefly. Okay, so now data flow modeling. As I said, it will deal with how the data flows between inputs and outputs using the Boolean expressions and operators. Okay, so it uses a keyword called assign. Okay, assign is used in the data flow modeling. Why we use data flow modeling is because it's very easy to write, easy to understand, and it can be easy to simulate in the gate level compared to gate level. Okay, and if you're using combinational logic, then it is very easy to describe the combinational logic in the data flow modeling. It can also be synthesized into ASIC or FPGA design. That means you can dump the code directly onto the FPGAs. Okay, so this is how it looks. First, assign is a keyword, as I told. Assign, then what is your output equal to what is your expression. Suppose you're building an AND gate, then assign y is equal to A and B. A and B does the AND operation, correct? So 2 input AND gate. So A and B are the inputs, Y is the output. So simple, in one sentence, you can describe the functionality of AND gate. So this is how it looks within the module. So my module is a keyword, and each module ends with an end module, right? Then what is the module name? Module name is AND gate. Now, what are the inputs and outputs that are declared as the port list? So my input is A, B, and output is Y. Now I have to describe Y in terms of A and B. Okay, so gate level abstraction and structural level both are same. No, dear, gate level abstraction and structural is very much different. Okay, gate level you will describe in terms of logic gates, AND gate, NOT gate, NOR gate, XOR gate, etc. Okay, structural level, what happens? You will describe the functionality of AND gate within one module, and you will use that module inside your top module. Okay, so that is the difference between gate level and structural level. I will show you the difference also. Okay, so I hope you understood the data flow modeling. Now, behavioral modeling, it will tell you how the circuit behaves. We are not aware of what goes on internally within the circuit. We don't know what is happening, what functionality it is doing. We only know If it is a AND gate, it should be A and B. So that is, if it is 1, 1, then it is high. Otherwise, it is 0. That is how the truth table of AND gate works, right? That is what we know about the circuit. So how do we develop that logic using the behavioral level modeling? Okay, that is the major aim of this behavioral level. And it uses, just like our data flow used assign, here we use always blocks, and within the always blocks we use if else statements or case statements or for loops, while loops, everything within the always blocks. Okay, so if you have a complex algorithms like the finite state machines, digital signal processing, then behavioral level modeling is very much easier to build. Okay, so this is how the behavioral level modeling looks like. So always is a keyword at sensitivity list. This sensitivity list means that upon what changes, suppose you have two inputs, A and B. If any of the input A and B changes, my output should change. That is my concern. So the sensitivity list will then be my inputs A and B. Okay, so based on this sensitivity list, my output within this always block will be changing. Okay, suppose you have your counter. For counter, we have clock reset as input and count is the output, which is a 4-bit. Okay, now whenever the clock is high, the clock is positive and reset is also positive. If either of these cases, if reset is high, it will check my clock is high or reset is high. Okay, if any of this is high, then it will check if reset is high or not again. And if it is high, then it is 0. Correct? So if reset, then count is 0. If reset is 0, then what should happen? Count should increment. So initially it was 0, then it will become count plus 1, that is 1. So if reset, count is 0. If reset is 0, then count becomes 1. When this happens, when either the clock is high or the reset is high. In either of these cases, this logic will take place. That is how behavioral modeling works. Now, gate level modeling, as I said, it uses logic gates to implement the logic. Okay, logic gates, like directly we use the keywords and, or, not, XOR, etc. Okay, you don't have to break your heads using whether it should be A and B in the symbol ampersand or A pipe B for the OR gate. Okay, so you can directly use the keywords and, or, not, etc. Okay, so this is the lowest abstraction level. Okay, so but it will be more detailed than the data flow, because in data flow you are deciding whether it is A and B or A or B by the expressions. So if you miss, instead of ampersand, if you write a pipe or negation symbol, then your entire logic will be different. But here, since you're using primitive gates like and, or, not, etc., it will be more detailed. Okay. You want me to explain behavioral once more? Okay, fine. Okay, see, behavioral modeling, as I said, it shows how the circuit should behave, what the circuit does. Okay, we don't know how many gates are there, what it does, how it does. Suppose you have a truth table of an OR gate. What is an OR gate? OR gate is output is high when either of the input is high. If both the inputs are 0, then it is 0. Right. So I should be knowing when my input is 0, 0, what happens to my output. When it is 0, 1, what happens to my output. This is what I know. Okay. So this we try to implement in terms of always inside the always blocks. So this is the syntax of the behavioral modeling, where always is the keyword. Okay. Always is a keyword. Then within the sensitivity list, we write what changes the output. Your A and B changes your output Y. So A and B will come inside this sensitivity list, or based on your clock and reset, my count is changing. So clock reset will come inside this always sensitivity block. Okay. So this sensitivity list decides what happens to my output. Okay. So if you have multiple statements within the always, so it should always start with begin and end with end. So this is very important. Suppose you have only one statement, then it is not necessary. But you have multiple statements within the always, then it should be started with begin and end with end. Okay, hope you understood now. Okay. So gate level modeling. So this is the syntax of the gate level modeling. What is the gate type that you're going to design? You have to give some name to that gate and what is the output and input of that gate. And this port list is very important because the output always comes first, then followed by inputs. Okay, so gate here I'm deciding AND gate. The gate name is G1. This is as per your interest. You can give either G1, G2, A1, A2, anything. This is just a name given to that one particular gate because I might have hundreds and thousands of AND gates within my circuits. Okay, so if I want to differentiate between the first gate and the last gate, how will I do it? If I don't give this name, every AND gate will be assumed as one AND gate only, right? So in order to differentiate between these gates, we are using this instance name. Okay, so first gate, we call it as G1, then second gate, G2, like that. Okay, and here Y is my output, A and B are my inputs. Okay, so Y is equal to A and B is the AND operation, and this expression here will perform that operation. Okay, so this is how you use inside the module AND gate. Here you should be very careful. This module name cannot be AND because AND is a keyword here. It means it is an AND gate. In itself, it means an AND gate. So you cannot use that primitive here in the module name. Here you have to give a different name than this primitives what you use here. Okay, so AND underscore gate, inputs A and B, output Y. See, here you can interchange inputs and outputs within the module ports. But here when you're declaring gate level modeling, the first one is always the output. Next follows the inputs. These inputs can be in any order. Okay, so AND G1 Y A B. So this will perform the AND operation. Y is equal to A and B. Okay, now structural modeling. Structural modeling follows the hierarchical design, either top-down or bottom-up approach, right? So as I told, we can use always blocks, if else, anything. First, we need to design one low-level circuit. Use that circuit in the top-level module. Okay, so this is the syntax. First, we have a module and end module. Module name should be given, inputs and outputs in any order. And within that module, we need to instantiate a submodule, what we have designed. That submodule name should be there. What instance, some name of that module should be given. And that port connections. These ports should be connected to these module ports. Okay. Suppose, for example, see here, I've given half adder. Half adder is the module. Half adder can be built using XOR and AND gates, right? I hope you know that half adder can be built using XOR and AND gates. So for half adder, the inputs are A and B. Output is sum and carry. Now I have an XOR gate. See, I have given XOR gate here. XOR gate inputs are A, B, and Y. This is the operation that is performed by XOR gate. Y is equal to A XOR B. The symbol means XOR. Okay. So this is the operation performed by XOR gate. Now I want to use this XOR gate in the top module half adder. So the name of the XOR gate is XOR underscore gate. I'll give some name to that XOR gate to differentiate it between the different modules. Now I have to combine or connect this inputs A, B, sum, carry here with the XOR gate A, B, Y. Okay, so inputs are A and B. So here A and B are inputs. Output is here Y. So since XOR gate is performing the sum operation, I'm connecting that Y to sum. So this port connections can be done in two ways, port mapping by name or port mapping by order. So I'm not discussing that right now. I just want to show you this syntax here. Okay, so this main module inputs and outputs are connected with the submodule input and output. Similarly, for AND gate, inputs are A, B, and Y, and it is doing the AND operation. So name of this is AND underscore gate. So AND underscore gate, since I have already used U1 here, I have to use some different name other than this. Okay, so I'm using U2. Similarly, I'm connecting the inputs and outputs of this. Since XOR gate gives me the sum output for the half adder, and AND gate gives the carry output for the half adder. So I'm connecting Y to the carry output. Okay. Hope you understood how the structural level modeling works. So half adder is the main module. Half adder can be built using the XOR and AND gates. So XOR and AND are the sub modules. I'm instantiating those sub modules within this main module. Okay. So this is how the instantiation works. And now switch level modeling. Switch level modeling is the lowest level modeling that is used in the Verilog. It directly works with the transistor levels like PMOS, NMOS, CMOS. Okay, so how the transistors can be defined inside the gates, that is done using switch level modeling. For example, like this, NMOS, we give some name again. And first, this order of this is important. First is drain, then comes the source, and then comes the gate. Okay, so in this order itself, you have to know. Suppose you have tens and hundreds of transistors, so it becomes very difficult to identify which drain is connected where, which source is connected where. Correct. So that is why switch level modeling is not much used. So we use all the other types as per our requirements. Okay. For example, see inverter, we have one PMOS and one NMOS. Correct. So first supply is 1 and supply 0 should be defined. Supply 1 is nothing but VDD. Supply 0 is nothing but ground, right? So for PMOS, what happens? Output is connected, output is Y, and source and gate is connected to input, drain is connected to output, source is connected to VDD, right? Upper level, right? So that is why PMOS, Y, VDD, A. For NMOS, the source is connected to ground. That is why instead of here VDD, we have written here ground. So you have to directly deal with the NMOS, PMOS in terms of switch level modeling. Now, suppose for example, AND gate, this is how 3 different levels of modeling looks like. For data flow, we have assign Y is equal to A and B, simple as that. Now, within behavioral modeling, you can write always at A comma B. This is the sensitivity list because as and when my A and B changes, I want my output Y to change, right? So this comes in the sensitivity list. Now, within begin and end, I am writing Y is equal to A and B. Instead of this, you can also use case statements. Case A comma B, 0, if it is 0, 0, what happens to my Y? If it is 0, 1, what happens to my Y? So like that also you can write. In gate level modeling again, since you know this is an AND gate, you can directly write a keyword AND, give some instance name, output and inputs. So this simple line performs the AND operation. So same structure, but different modeling styles. Okay. Now, in structural modeling, I have discussed about the instantiation. Screen is freezed. So is it out? Can you see it now? Okay. I hope you can see it. Okay. Okay. In structural modeling, I have discussed about the instantiation, right? So using the submodules within the top module. So what happens whenever a module is invoked, whenever you use that submodule, it creates one separate unique object which has its own name, its own variables, its own input and outputs. Okay, so this process of creating objects, we call it as instantiation. Okay, so this we call it as instantiation. That is why this instance name should be different, because each time this line is invoked, it will create one different object. Once it is, suppose here I have a module ripple carry counter. I'm using that ripple carry counter into some other module using the name of that ripple carry counter. I have used a name here. I've given the name as counter1, CNTR1, and I've given inputs and outputs. Okay. So now this again, same ripple carry counter, I can use multiple times. Just by changing this name and with connecting the input and output properly, I can use this ripple carry counter multiple times. Okay, so each time this is invoked, it will create a new object. It will assume it as a new object. It will create one object with its own variables. Okay, so we don't want to confuse the coding ourselves also giving the same names. Okay, because so you have to use this different instance names when you are instantiating. Now, Verilog supports multiple data types and operators. Okay, so I'm not going to discuss entire data types and operators in this session, because since this is a very short duration session, I'll be limiting myself to 1 or 2 data types and 1 or 2 operators. Okay, so now what is a data type? Data type is one kind of a storage format that is used to store something. Okay, or define the range or type of a particular variable. Okay, so there are 2 types. One is nets and one is variable. Nets, nothing but the wires. Between 2 AND gates, you have wire. So output of one AND gate is getting connected to input of the another AND gate. So this interconnection, we call it as wire or net. This is just a physical connection. Okay, there are multiple types of data types under net, which are called wire, W and WR, etc. Okay, and another type of data type is variable. So variable type means what? Variable by name itself, we can see that it keeps changing the values. Correct. So it is used to store some value in the circuit. Okay, so suppose we have a register type or integer type. Suppose you have a box and you keep a biscuit in that. You can remove that biscuit and keep something else in the same box. Correct. So box is same, but the item that you're placing into the box is different. Right? So that is how variable type works. It is used to just store the values. Okay. Now these data types that are used to represent the data storage elements. Correct. So it can take 4 types of values. So suppose you want to represent a logic 0 or a false condition, then it stores 0. If you want to represent a logic 1 or true condition, it stores 1. Suppose you want to represent unknown logic values, that means it can be either 0 or 1. We don't know what the value of the particular variable will be. Then it is X. Then Z represents the high impedance state. Now wire, as I told, it is just used to connect the elements. Nothing much. It doesn't store anything. It is just used to connect the elements. Okay. Here wire example. So this is the keyword wire W1, W2. So W1 is used to connect some maybe AND1 and AND2. W2 may be used to connect AND3 and AND4. Okay, just connecting 2 different blocks. And register data type, it is one of the variable data types just used to store the values. And this can be changed throughout the simulation. Okay, so suppose you have here reg A is equal to 1. Then within the always block, I will change A is equal to 10. So it can keep changing. It may not be same throughout the simulation. Okay, so registers are just used to store the elements. It can be overwritten throughout the simulation. Okay. And these are other types of data types, which I'm not going to discuss because of the short duration here. Okay, so integer, real, time, and here this integer is 32 bits and signed integer. Signed means what? It includes both positive and negative numbers. Real, it includes positive, negative, and floating points also. And time cannot be negative, right? So that is why it is unsigned. So like that string we have, if you want to show this words, hello world or your name, anything you want to display, then within this quotes, we write this text that we call it a string type. And arrays, it can be single, multi-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, anything can be there. Okay. And these are few operators that we have in the Verilog programming. Suppose consider this arithmetic operators. Suppose A is, I've given us 4-bit binary 0011. This notation means 4 bits. B is for binary. So 4 bits binary 0011. And B is 4 bits binary 0100. Now A plus B. So this is an arithmetic operator. It does multiplication, division, addition, subtraction, and modulus. So modulus will give you the remainder. So now A plus B will give me what? So 0011 is 3. 0100 is 4. Correct? So 3 plus 4 is 7. So it should give me 7. So A plus B will give me 7. A into B. This is multiply. Now 3 into 4. It should give me 12. So the answer is 12 here. B minus A, 4 minus 3, that is 1. So it gives me 1. And it adds and subtracts bit by bit. So 1 minus plus 0 is 1. 1 plus 0 is 1. Again, 0 plus 1 is 1. 0 plus 0 is 0. So that's how you get this output. For logical operators, here what it does is, suppose the value of a particular variable is more than 0, greater than 0, then it assumes it as logical 1. If it is 0, then it assumes it as logical 0. So here A is logic 1 and B is logic 0, right? Since A is greater than 0. So what this logical operation does is A logical AND of B. So 1 and 0. Since this is logical 1, I will take it as 1. This is 0, so I will take it as 0. So 1 AND of 0, what it gives me? 0. So AND gate means 1 and 0 is 0 only, no? So A and B is 0. Suppose you're doing OR operation. So since this is logic 1, since this is logic 0, 1 or 0. So if either of the input is 1, then my OR operation output will be 1. So A logical OR of B will give me 1. And negation of A, not of A. Sorry. So A here is logic 1. Since it is greater than 0, it is logical 1. So negation of logical 1 is what? Logic 0. So the output is 0 here. So remaining operators, that is for the some other webinar session, or if you join the course, then I can discuss in detail with it. Okay. Now it also, Verilog also has procedural constructs, specially used in behavioral modeling, called the initial and always blocks. Okay, so these are the very basic statements that we use in the behavioral modeling. Okay, so whatever logic you write, whatever functions you write, everything should come under these, within these blocks itself. Okay, so each will start at the same time but ends at different times. Okay, so it starts with initial simulation time 0. Each activity starts with simulation time 0 but ends at different times, because initial occurs only once during the entire simulation, but always keeps changing based on its sensitivity list. And always and initial cannot be nested together. You cannot use initial inside an always or always inside an initial. So this is an example of initial block. So here initializing M to 0. I'm just making M as 0 with this one statement within the initial. So since here only one statement is there, I'm not using begin and end. But if you have multiple statements, then you should use begin and end after the initial. And there is no end or end module like kind of thing for the initial. Okay. Now, this is for an example for always. Here, previously I have shown you always at passage clock. Okay, so but here we are just using always after 10. Clock is negation of clock. That means every 10 nanoseconds, the clock will become negative. If suppose my initial clock is 0, after 10 nanoseconds, it will become 1. Okay, again after 10 nanoseconds, it will become 0. So like that, it keeps toggling. This is how we use always and initial blocks. Now, let us design one simple circuit called 4-bit ALU. Okay, I'll be using model sim for this. Okay, so what is an ALU? ALU, we know it is within the CPU. It acts like a brain of the CPU. It performs arithmetic operations, logic operations, bitwise operations, right? Logic operations, I told you, AND or XOR, how to perform. And shift, left shift, right shift, negation, not of A, everything, right? So everything, how to perform, that I've explained to you. So ALU performs all these operations and then give the output to the other blocks within the CPU. Okay, now let us see how to design this ALU in the model sim. Okay. Just give me a minute. LSIM is taking some time to open up, so just bear with me for another 2-3 minutes. Okay, I'll show you how to do it. Okay, so this is the Model Sim platform. So first we need to go to File, then click on New, Source, select the since we can do with VHDL, Verilog, System Verilog, anything, but since we are using Verilog, I'll click on Verilog. Okay, so here you have to type the code. Okay, so first thing is module is the keyword, then name of the module, ALU. Since I'm designing an ALU, I will type ALU, then inputs and outputs of ALU. Okay, so I'm taking 4-bit inputs, so that will give me 4-bit output. Okay. Okay, video is lagging because we are using the software now, so it keeps lagging for a bit. So input A and B, and based on the select line, select is a 3-bit line I'm taking here. Okay, so based on this select, my ALU will perform either arithmetic or logic operations or bitwise operations. Okay, so I'm taking my output as out. See, my inputs are 4-bit. How do I represent it as? Within the square brackets, I've written 3:0. That means it will be starting from 0, 1, 2, 3. That is 4 bits each. Okay, so 4 bits A and B, 3 bits select line, and 4 bits output. Okay, so now what should be my sensitivity list here? Whether my A changes, whether my B changes, or if my select changes. So in either of these cases, my output should change, right? So on what basis I'm deciding which operation to perform? It is based on select line. So I'm taking case select. So whenever the select line changes accordingly as we are giving the numbers, so my output will be changed accordingly. Suppose my select is 3-bit 000. Then what should be my output? I'm assuming output will be A plus B. So this operations can be different. Okay, so you can decide what your ALU will do when select is 000. Okay, so when it is 001, my output is A minus B. And when it is 010, what it should do? When it is 011, what it should do? Everything you should decide while writing the case statements. Okay, so let me finish this. Yeah, I have muted it so that I can finish the coding. Okay. Let me finish the coding. I'll start talking. So I've completed writing the module. Okay, now we have to save it. So, okay, is my screen visible or is it lagging? Okay, okay. So now you have to save this code. Save this code in as a ALU.v that says it is a Verilog file. Okay, so okay, it's lagging. Okay, so since we have used case here, it should end with end case. And since we have used begin statement, why we have used begin? Because we have multiple statements under always. So we have used begin. So once it starts with begin, it should end with an end. Okay, case should end with end case. There is no spaces between end and case, and begin should end with end. And now module should end with end module. Okay, so now my designing part is done. Okay, now we have to verify this. How do we verify this? We have to write something called test bench where we will give the values for A and B. Okay, so for different values of A and B and for different values of select, we will decide what operation it should do. Okay, so we'll give the values for select from 000 to 111 and then we try to simulate the file. Okay, so let me just complete the test bench. Okay. Those who didn't get mail means I think those who have registered, you would have already got the mail. Right. So any which ways, we will be sending the feedback form at the end of this session. Okay. Once you fill that with a proper working email IDs, you will receive your e-certificate by tomorrow. Okay. And why output variable is wire? See, we are changing the values of A and B constantly. Correct. And select also. So we are deciding it as reg. As I told, it is a variable type. Register is a variable type. If we can change the values throughout the simulation. But output based on this values only it is changing. Otherwise, it is constant. It is just some wire that connects from the output of the ALU to something else. Just a wire. Okay, just a net. That is why it is declared as wire. Hope you understood. See, as you can see in the test bench, again, it starts with module, some module name. Here, you don't have to declare anything within the ports. Okay, even this brackets is optional. You can just write module name and put a semicolon here. So each statement should end with a semicolon, except these always initial begin end keywords. So each statement should end with a semicolon. Okay, so after declaring the inputs and outputs, here in test bench, we declare it as registers or wires. All inputs are declared as registers because we keep changing the values, and all outputs are declared as wires. And after this inputs and outputs are declared, you have to instantiate the main module within this test bench, because the main module ALU is what we are going to test. So that has to be included in this test bench module. Correct. So that is why we are using the ALU module. This is the name of the ALU, what we have given. So this is the instance name, just some name. Here I'm using DUT, that means design under test. You can use A1, A2, B1, B2, any name of your choice. And here I am connecting the ports. So this I am not using dot A of A. Here I'm directly writing A, B cell out. This is nothing called port mapping by order. This should be in order with your main module. In your main module, if you have given A first, B second, select third, and out as fourth variable, fourth port, then it should be in that order only. So that is the disadvantage of this port mapping by order. So suppose if you are using dot A of A, then even if you interchange A to the fourth output and out to the first output, first port, then that doesn't matter, because you're mapping with the names. A is mapped to A, B is mapped to B. But here, if you interchange the order, then it will create a problem. So after this, we are starting initial. So at first, as soon as the simulation starts, what we have to make is A is equal to this value, B is this value, and select is this value. So this is my initial values. After 10 nanoseconds, I'm changing my select to 001. Again, after 10 nanoseconds, I'm changing select to 010. So like this, I'm changing from 000 to 111. Okay, so this dump file, dump.vcd, as many people are asking. So this we are using to generate the waveforms. So, okay, so this is the value change dump file that will be saved in the system. Okay, this is particularly used when we are dealing with the EDA playground. Okay, so EDA playground will not give you waveforms if you don't write this dump file dump words. Okay, it is mainly used to generate the waveforms. Okay, so after giving these values, I want to monitor the values. So when my select is 000, what is A and B and what is my out? So I'm using $monitor. Okay, so these things we'll be discussing in the classes or in the next webinar if possible. Okay, so $monitor, it as soon as the simulation starts, from the starting till the end of the simulation, it keeps monitoring these values A, B, cell, out. Okay, and it keeps updating this in the descriptions. Okay, so once you have written the test bench, you have instantiated the main module, you have to save this file. I'll give some name as alu_tb.v and save it. Okay. Oh, is it visible or lagging? Okay, let's update it. Okay, now you have on your left side, you can see the work folder, right? So here we had previously saved file, so I've deleted it. So after writing the file and saving it, you have to go to the compile. Okay, compile, then compile again. Select the files you want to compile one by one. First ALU, whatever name you have given, you have to select that. Then compilation is done without errors, as you can see in the bottom. Error 0, warnings 1. Okay, warnings 0, sorry. Okay, then you have to compile the test bench also. So go to compile again, compile, then select the test bench, then compile. Okay, so again, test bench is with 0 errors, 0 warnings. Now compilation is done. Okay, you have checked for the errors and warnings. Now we have to see the waveforms. Generate a waveform that is called simulation, so that we can check if my output is correct. So right click on the test bench, because that test bench is where you are giving the values for A and B and select lines. So right click on the ALU test bench and click on simulate. It will take you to another waveform window. Okay. So here three things will be there. One is your main file, test bench file, and wave. In under wave, you will see this waveform. Here select on this inputs and outputs. Okay, right click and add waves. That is sent to waveform window. Okay, now click on run. As you can see, we have generated a waveform. So here you can verify if my output is correct or not. So suppose 0, 0, 0, when select is 0, 0, 0, my input is 1, 1, 1, 0, 1, 0, 1, 0. So what should be my output? 0, 0, 0, we are adding it. So 0 plus 0 is 0. 1 plus 1 is 0, 1. So 0 here, carry goes here. 1 plus 1 again 0, 1. 0 here, carry goes here. So 1 plus 1 plus 1. So that is 3. That is 1, 1. So 1 and carry out is left out. Carry is neglected. So the output is 1, 0, 0, 0. So this is correct. So like this, you can check for each and every calculate like select line values if my output is correct or not. Okay. So, and we have used $monitor in our program. So what it does is here in the transcript, you can see after the simulation is started, it starts checking the values. What is A in terms of decimals, because we are using %D. D is for decimal. So A is 14, B is 10, select is 0. So I have to add. So my output is given in terms of, in binary, it is 1000 means it's 8. So that is given as decimal 8 because the carry is neglected here. Okay. So that is how it is checked. Hope you understood how it works, right? UUT and DUT is different in a test bench. No, UUT, DUT just means unit under test and design under test. That is just an instance name that you are giving. Okay, so nothing difference. So we are using, you can use Xilinx Vivado also, EDA Playground also. Okay, and you can use Quarters also. We have a tool called Synopsys, so we can use that also. Okay, so you can use any tool to simulate. We are just using Model Sim. Okay. Okay. Hope you understood how to simulate, design and simulate, right? Okay. Now, so what is the difference between simulation and synthesis? So simulation, as you've seen just now, after writing a design, you can verify whether your design is behaving as per your requirements. That is the main purpose of simulation. Whereas synthesis, it will convert your design into logic gates. Okay, in terms of AND gate, OR gate, NOT gates, etc. Okay, so simulation uses all kinds of Verilog constructs, always initial, but synthesis has some limitations on which constructs it should be used, whether it is convertible into a hardware or not. Okay, so simulation here I've mentioned only two, Model Sim and VCS. You can use any other tool available, even the free resources. Okay, for synthesis, we will be using Synopsys Design Compiler. Okay, so, tool from Synopsys. Okay, so simulation, you can use waveform, see the waveforms and debug the information. Whereas synthesis, you will get gate level designs. Now, there are certain RTL coding guidelines that we should follow while designing a circuit. So I'm not going to discuss these coding guidelines completely, but one such thing is avoid incomplete sensitivity list. Okay, so sensitivity list, we know always at A comma B. Suppose if you miss B in the sensitivity list, and if your output is Y is equal to A plus B, so your Y is changing as long as A and B, anything is changing, but you have not included the B in sensitivity list. So even if your B changes, your output will not change. So that will give you an error. Right. So we should avoid incomplete sensitivity list or include all the variables, all the input variables that are available within the sensitivity list. Okay. And for every case statement, we should always include a default case. Okay, suppose I have used the select lines from 0, 0, 0 to 1, 1, 0. That is 6. I have not used the value 1, 1, 1. So what will happen? So we don't, the tool doesn't know what output it should give at for the select line 1, 1, 1. So it will show some error. But actually, I wanted it to be shown 0, 0 or 1, 1. So I will not get what the actual value I required. So that is why we have to declare a default case wherein we decide what the output should be if none of the inputs matches. Okay, so all these coding guidelines will be taught to you in detail in the class. Okay. Now, these are the courses that are offered at RSA, especially for VLSI. Okay, so we have advanced analog layout design, ASIC RTL design verification, physical design and verification, ASIC prototyping on FPGA. So analog design, RTL design verification, physical design verification, these are 6 months courses. Okay, well, you will be taught from basics till advanced of all these concepts. Okay, analog layout special, the major focus of this course is the FinFETs and how to design, how to draw a schematic and how to draw the layout, how to do the verification, everything will be taught in analog layout design. Okay, and in RTL design verification, starting from Verilog HDL, digital design concepts, how to design the circuits, how to verify it using the system Verilog, and how to use the UVM methodology, everything will be taught to you in the 6 months course. And physical design verification also, like I said, synthesis, turning your design into logic gates. Once it is generated, then we use that netlist file as the input for the physical design process and take it through the complete physical design flow from floor planning till we generate the GDS2 file. So all this will be done within the physical design course. Okay. So, and ASIC prototyping, you will be learning the ASIC flow, FPGA flow. Okay. And also how to dump your codes on the FPGAs. So an FPGA implementation with Verilog and RTL verification using system Verilog. These two are short duration courses, 1 month courses, which is meant for people who are looking for short-term internships kind of thing. Okay, so in FPGA implementation, you will be taught with the Verilog HDL along with the how to work with FPGAs. Okay, RTL verification using system Verilog. This is again 1 month course where the basic requirement is that you must know some little knowledge about the Verilog. Then we can teach you how to code using the system Verilog, how to verify using system Verilog. May not be completely because system Verilog in itself takes 4 or 5 months to learn. So that is how we have a 6 months course called RTL design verification. Okay, so this is just a crash course kind of thing. Okay, and apart from VLSI, we also offer embedded and software engineering courses also. As you can see, we have different duration courses, 6 months, 4 months, 2 months, and 1 month courses in embedded and software engineering. If you visit our website, you can go through all this indicative content of each and every course. Okay, you can see which is relevant to you and you can reach out to us if you're interested in anything. Okay, so at RSA, this is what we offer. Infrastructure that is available. Okay, so whatever the software you are getting, you will be given access to these softwares like Synopsys, Cadence, so etc. So 24/7 access will be given. And industrial grade components, whatever the industry is using right now, that particular components only we will be using, that tools only we are using, and it is completely project based learning. So you will be given projects that are industry relevant, that is real-time projects. Okay, so the projects that have been done in the previous batches will not be repeated for the current batch. Okay, so we are focusing on giving you some projects that adds some value to your resume so that you will be confident enough to attend the interviews. Okay, so we have trainers where they are trained from industry people. Okay, so they will be teaching you. We have well-established laboratories that you can work beyond the office hours. Okay, so you can access the tools, everything. Okay, so these are the website and social media links of RSA. Okay, so you can visit these links and check out the projects, everything is done, and our courses in website, you can check with the indicative content of the courses. Okay, if you're interested in any course, you can get back to us, we will guide you through it. Okay, and one announcement, another webinar called FPGA implementation is going to happen on Thursday. So here in this session, what we have done is we have designed an ALU using Verilog. So we have simulated it using model sim. Using the simulation waveforms, we have checked if my output is correct or not. But how do you check that on a real hardware? How do you dump that onto FPGA and check on FPGA if my ALU is performing correctly or not? Right? So that particularly will be taught you in this webinar session on FPGA implementation. That is happening on 13th June, Friday, 5 p.m. same time. Okay, so if you're interested to learn about the FPGA implementation, please do register. Anyways, this registration link, everything will be shared to you in the WhatsApp group. Okay, so you can register for it. So if you have any other questions, we can discuss now. Yeah, GVim is just an text editor, so you can have anything. Hello, everyone. Very good evening. Before I start my meeting, just let me know if I am audible. You can text and say. Okay, thank you. Thank you, Kirtana. Okay. So I am Priyanka.